Okay, let's get started. I'm Geoff Hoffer with Aztech Geothermal. I'll be moderating this panel. We have a fun topic. We'll be going over geothermal Borefield quality assurance with some panelists here with plenty of years experience. And I just think it's important to point out one thing with the names up here. Not often you see two Geoffs in the same room that both spell their name correctly. So we had to import them from the UK, but we made it happen. So write that one down. And I'm glad John Chavaco left because I'm going to do something. I'm probably going to get in trouble if he watches the video. As a moderator, I'm going to step out of bounds. But I had to take this chance to bring in a couple display items. And this is some stuff that we found in the field. We're primarily residential contractors. We service a lot of older systems. So my guys bring me back samples of stuff that we find in some of our ground loops. So I thought it would be fun to bring in. So these are two items that we found in the inside piping of a house, 30-year-old system. We replaced the heat pump, and then the homeowner was complaining about every time we staged our circulators up to a higher speed, they heard this rattling sound in the pipe. And it took us a couple of visits to figure out that there was this rock in the pipe. And, might not be able to see it in the back of the room, but every time the pump speed ramped up, this was sitting on a valve, and then it went up to a barb fitting, rattled around. Every time it set down, it went back down, cut the pipe open, found a rock in there. So been in the system for 30 years, fun to find. And then once we got the flow rates up, the first time they ran the flow center, they heard a dink, 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 dink all the way across the basement in a pipe. And they looked in, there was non-pressurized flow center, so they could look in the bottom of the canister. We found a screw that came out of the ground loop. So where did that come from 30 years later? Then recently we had a system that's about 10 years old. Circulator rotted out off the flow center, so we had to replace the whole flow center. And we said, well, if we're going to do that, we better check and see what's in the ground loop. So we flushed the whole ground loop. This is what was in the ground loop. And earlier today, it had all the sediment in the bottom of it. We just flipped it over, and it became brown again. So we got rid of all the solution that was in the ground loop. And then, of course, when we flushed that, we found a screw in that ground loop as well. So it's been there for 10 years. So it's kind of amazing what you can find out in the systems if they're not installed correctly and flushed correctly. So we're going to get started here. I believe Kate is first up. So we'll swap name tags and you can take it over.
Thank you so much. Hi, everybody. Oh. Okay, if I'm talking too loud or too fast, somebody just give me a hand signal because John, he's not here, but he warned me extensively to not talk too quickly during this session. Thank you. And then that's next. Excellent. My name is Cheng. If you guys, John's here. Thanks, Brock. If you guys don't know me, my name is Kate. I'm from Geosource Energy. Geosource is a bit of a new player on the block in New York. We've been around for just a couple years now, but we're not new to the geothermal space. We were founded in Canada 21 years ago. We're a dedicated geothermal contractor. We came up in the Greater Toronto Area market, which is a very urban geothermal market. There's great market penetration for geothermal there. One in three new construction buildings have geothermal. And on an average basis, there's 222 cranes working in the city on an annual basis. So that's a lot of projects. I'm here today to talk about Borefield quality assurance, and some of our panelists here are going to be covering a wide swath of topics related to QA, but I'm specifically going to speak about grouting and the importance of having a properly grouted borehole in your system. One thing that I do want to mention for those of you here that haven't been to a site to see drilling happen, if you're working with geothermal systems, it's really, really important and useful to go and actually watch the drilling process happen to understand when people are talking about looping and grouting and tremie lines and how to flush and fill your system, really what that means. Recently, our CEO was working on the ANSI CSA 448 rewrite. And he had the CSA folks come to a site in Canada to actually see geothermal drilling and to see tie-in. They had never seen it before, and they'd been kind of working on this committee for a long time, and it changed a lot of their perspective on some of the policy decisions that they were making. So I would just recommend, there's a lot of drillers here. If you have the opportunity to reach out to them, see if you can do a site visit and just really get immersed in drilling on site to see how it works. Okay, so I'm going to do a really quick presentation about how you grout a borehole properly and get a proper full column of grout from the bottom to the top. This is one of the most difficult and important factors in a quality installation to achieve, and it's very important. So a little bit of a process overview starts with a controlled, so once you've drilled the borehole, and you're starting to grout, you want to do a controlled insertion of the loop. You want to get your tremie line and your loop down together. You want to start grouting in the rock from the bottom to the top. When you're doing casing, you want to be grouting from the bottom of the casing and pulling that casing as you're grouting from the bottom to the top. How you complete your loops during construction and what grout testing is required during installation. Okay, so we have a picture here. It's a picture that you never want to recreate. This was an accident that happened on one of our sites a few years ago. It's not something we're proud of, but I think it presents a interesting learning opportunity for everyone that works with loops. So when you insert a loop into a borehole, you want to make sure that there's water in the loop and water in the borehole. Why? Because if you have water loop and no water in the borehole, that's a lot of weight on the loop, and it can cause it to take off like this down a borehole. So this is an 850-foot borehole with 1.5-inch loop, and it fully took off on our guys because they forgot to put water in that borehole. I guarantee you they are never going to forget that again. And if you have water in the borehole and not in the loop, you risk collapsing the loop because there's air in the loop, and that, sorry, I'm fogging up my glasses here. You risk collapsing the loop, and also it floats, so it's very difficult to get it into the borehole. We do recommend using a pusher to push the loop instead of pulling it, having it pull by its own weight down. I saw a couple great examples of pushers from some of the vendors that are here. We made our own many years ago. You can kind of see it on the side there, but that really helps get the tremie line and the loop down. And it really is the only way to do small diameter boreholes. So generally when we drill an 1.25-inch loop, we're drilling a 3 7/8-inch borehole, which is a very small, tight borehole. But it does allow us to get the full loop plus the tremie line down. And that does give you a better connection with the ground, and you use less grout. You use less grout when you're drilling a small diameter borehole. How do you get the tremie line in? So the only way to grout those small diameter borehole is to push the tremie line and the loop together. Generally, we're connecting the tremie line to the loop just a few feet off of the bottom so that you can start grouting really from the bottom of the borehole. You need to be able to retrieve that tremie line, obviously. And you kind of have to find a technique to make sure that you can get it down because it does tend to want to float. So whether that's adding water, using air to pull out some water so that you can get it down a little bit more. There are different techniques of doing that, but it is important. I will pinpoint that our tremie line sits within a sea can, so we have a modified sea container that all the grouting operations happen within, and that does help with dust management on site. We have been on several sites where people are concerned about the flake in the grout. It's usually like graphite, but they get really worried when they see a silver flake, and so having it contained within that will really help just prevent the spread of dust. When you're grouting in the rock, so below casing, your tremie line should be just shy of the bottom. You want to have your grout stacked from the bottom of the borehole to ensure you have connectivity between the loop and the ground. Anecdotally, I will say that Geosource 15 years ago, we bid a project and we weren't the low price, so they awarded it to someone else. But that same developer came back to us just last year and said, there's something wrong with our loops. Our system's not functioning the way it should be. And after a lot of analysis, what they determined was they actually didn't grout the boreholes properly. So you won't notice the effects right away in your system, but over time, it will decline in terms of the capacity that you're able to serve. And that will present a very difficult problem later because it usually involves almost double the amount of CapEx that you need to have your system maintain its longevity because you need to drill new boreholes. Once you've grouted a hole, you're not going back. There's just no way of getting that done. So it's important to do it right the first time. When you're grouting while pulling casing, so you'll grout to the bottom of the casing. Our drills pull casing because they're dual rotary, so we always set casing and then we pull it. But before we pull the casing, we want to make sure that it's flushed and that we start grouting. The grout is filled to the top of the casing before we pull it out. So usually we have to let the grout set in the rock before we start pulling casing, because if you do pull casing before the grout set, you risk pulling the loop and pulling the grout. So you want to make sure the casing doesn't have grout in it. You want to flush it. And then when you're ready to pull the casing, you want to grout from the bottom of the casing. So you make sure that your tremie line is still in the grout stack. You want to grout from the bottom of the casing, pull the casing prior to the grout setting up, because if the grout sets and then you try and pull casing, you're going to pull your loop and you're going to stretch it out. And you want to top off your grout as you pull casing sections. So every time you pull a casing section, the grout is going to displace a little bit. You want to top that off before you pull the next section. At the end, once you've grouted that borehole, it's fully grouted. The way to complete loops during construction, especially if geothermal comes early during construction, often you'll see loops sticking out of the ground, like on the left there. In a lot of the urban sites that we drill, it's important to kind of maintain that excavation space or construction area for the contractors to work in. So what we often do is we plug the loops below grade and then we cut them off internally. It stops the debris from getting the work, but it also allows us to keep that excavation area void. And then what you see on the right here is once we've pulled the rest of the loop after plugging it at grade below the lowest grade, you'll kind of have a hole there that's empty, but it allows all the other contractors to work on that site without damaging your loops, which is very important. Last slide, grout testing during installation. This is important. It's generally determined by the engineer's specification. We've seen specifications that are very intense with testing requirements, like twice a borehole. I will caution that doing that, although it does guarantee you have good grout, it also increases the cost of that borehole significantly. And increased testing means increased cost and time. Also, like samples that you take, there's a lot of variability within the mixture because it's not a solution. So generally within one sample, they'll test like 4-5 times almost in that one sample to check the numbers to make sure that you're getting the conductivity that you need. Generally recommend testing in the first few boreholes because if you have an issue with your grout, you don't want to be testing that on the 10th one and then realizing that you have an issue with your previous holes. So we recommend testing that first hole, doing a second test within the first 10 boreholes, and then at minimum, according to the standard, when you're doing 50 plus borehole installations, you need to have at least 33 tests per 50 boreholes. So that would be really a minimum. We would recommend testing 10 to 20% of your boreholes if you have the capacity and budget to do that. And that's it on grouting. Thank you so much.
Yeah.
Yep.
Hi, everybody. My name is Geoff Ellison. I'm from UK. I have a plant hire business and also a renewable energy company, and we also do drilling. And I sit on the British Drilling Association's Technical Standards Committee. And I've come to chat really about how we automatically test the loops that we put in the ground. So loop testing, why do we do it? Well, the things we need to prove really are, first of all, does it leak? Secondly, does the fluid flow through the pipework as designed? Where is it? That's always useful. And also, can we trust the results that we get? So a ground source heat test regime has to have the following parameters, really. First of all, it must be relevant. We only want to test for things that are useful. It's got to be accurate. All the sensors that we use on the system have to be in calibration. It's got to be consistent. It doesn't matter who does the test or where the test is undertaken. We want to get the same answer. It should also be repeatable. If you do the test a second time, you should get the same answer that you got the first. And finally, it should be safe. We're working at pressures of 100 psi, sometimes more than that. That can be dangerous if you get an uncontrolled release of fluid, but I'll deal with that a little bit later on. So the pressure test, that's to see if the thing leaks. And as you know, polyethylene pipe suffers from a concept called viscoelastic stress or creep. When you pressurize it, it expands, and that affects the results. So we have a couple of test regimes here. You have your own standard, the ASTM 42164, and we have a British European standard, which is BSEN 805. Both standards say you should flush and degas. Our standard in the UK says 15 minutes. Yours doesn't specify that. You then, in the American test, you raise and hold the test pressure for 4 hours. That's usually a default pressure of 100 psi. And then after 4 hours, you drop that pressure by 10 psi, and you monitor it then for 60 minutes. If your pressure doesn't decrease by more than 5%, then that's a test that passes. That's taking you 5 hours to undertake. In the European standard, we have a 15-minute purge cycle. We then hold the pressure, the test pressure, for 10 minutes and 10 minutes only, and then we leave it for 1 hour. After 1 hour, we drop the pressure by 10%, and if the pressure decreases by less than 1.47 psi, it passes. We can extend the test to a further 60 minutes. At that point, the test pressure pass mark is 3.7 psi. So that's the difference between the two. So that is the way that the European standard actually looks. So I think I can show you. Can you see that? Is that visible? Just? Okay, we raise the test pressure to our target test pressure there. You can see that. Is that a better one? That's better, yeah. Don't poke it in your eye. Okay, we raise the test pressure to the test pressure itself there. As it's the test pressure, the pump goes down and the pressure decreases. So we have this 10 minutes of pumping it up. Then we let it naturally decay for 1 hour. If you've got a significant leak, that pressure drops like a stone, so you know you failed already. After 1 hour, we then drop it by 10%, and we see the pipe rebound, and we remeasure the pressure between 10 and 20 minutes, 10 and 30 minutes into that system. If it drops by less than 1.47 psi, then it passes the test. So your loop has passed its pressure test, so now you need to do a second test to make sure that the fluid passes through it at the right flow rate. So, what can affect the flow rate? If you have obstructions in there, that's going to reduce the flow rate. We've already seen Geoff show us a piece of rock and a couple of screws. That won't have helped. But also, if you've got any kinks in there, if you twisted the pipe or bent it on the way down there, you may not notice that when you put it in, but that will restrict the flow. Now, in the UK, we have a situation where we have to compare the flow rate on the feed and return pipe when we put a known flow rate through it, and we have to also do that without disconnecting the pipe work. And we then can compare the feed and return flow rate, and that will then determine whether or not we've got any restrictions of the flow itself. So we need apparatus really to test the loop at the point of installation to make sure that it complies with those test criteria. So what do we need? Well, if we look at the features of an automated system, first of all, we need degassing tanks to remove the air and any solids that we may have accumulated in the pipes itself. We need to use clean water. Now, I don't often find clean water on drilling sites. I wouldn't drink it. So we have a process there where we can sterilize it with UV light and filter it to make sure that the fluid we're putting into the borehole contains no solids, also contains no bugs. We can then undertake the pressure in line with the American or the European standard, depending which is your particular forte on that. And we will carry out the flow test in both directions without disconnecting the pipework. All the results are taken electronically, stored and exported. Nobody can manipulate those results, they're accurate. And we also record the loop position by GPS, so we know exactly where it is. And finally, we have camera supervision inside the unit for customer support, but also outside the unit to make sure that we're testing the pipe itself and somebody isn't using a bogus piece of pipe to get around the system. So what does it look like? That's the unit on the inside. We have degassing tanks, 2 of them, to make sure we get the air out of the system. A motive pump. We have a pressure release valve there, so we can't overpressurize the system and damage the loop. On the other side of the unit, we have the filtration system, water treatment, and all the pipe work. If we look at that in closer detail, there we have a filtration system which goes down to 10 microns. If you get down to that level, then the UV sterilizer will eliminate any bacteria. So we're dealing with totally clean water going into the borehole itself. On this side, that's the pipe work and the instrumentation side. So when we have the liquid coming from the pump, comes down this one, out into the loop, comes back on the return line, and then back to the tanks. And then we can rotate those valves around. So in that situation, it comes from the pump, diverts that way, out to the loop, comes back in, and then goes back on that bore field that way. So we can rotate the direction of the flow without anybody touching it. So that's what it looks like on the outside. Yes, it looks like a horse box because it is a horse box. Okay? We've just put it in there. It's a secure container. What you will notice about the pipework coming out there is we've shielded it. We have to do that under UK law because any pressure test is classed as a hazardous operation. So we have to shield everything we've got outside the unit with 3mm plate steel. What we do there is we paint it white. The reason we do that is it reflects the sunlight. This is a test that takes maybe 2-3 hours. So if you've got sunlight interference there, you're going to affect your results. We also insulate that inside of the shield to prevent temperature interference. Now, I've worked in Minnesota in the winter, and I've also worked in Phoenix in the summer. You guys have some real serious temperature issues. We don't have those in the UK, okay? Our temperature is fairly constant all year round. So in summary, what do we want? We want something that's easy to use. All the guy who operates this unit has to do is program the test pressure and also the flow rate, press the start button, and then he walks away. If you can cook a microwave meal, you can use this system, okay? Dead simple. Secondly, it's got to be robust. I employ drillers. Drillers can sometimes be a bit brutal with their equipment. My drillers have used this, they can't break it, and they also say it's a good system, it makes life easier for them. The results are accurate. Nobody's going to contest those because they've been done on a calibrated piece of equipment. They're incorruptible. It means the data there you can trust. It can be used for guarantees, warranties. It also can be used for an accurate database. It's safe. All our pipework is shielded, it's insulated, so there can be no danger from that. And there are two other factors we're working on for the next generation of testing, and that's one to confirm the depth of the loop itself, and also one to confirm its verticality. When you drill, it doesn't go straight down, and we get deviation due to different geological strata, and so we end up with something that's not vertical. So we have a system there we can actually work out a three-dimensional plan of the bore field, which means we can then pass that back to the designer, and if there's any areas where boreholes are competing with each other, we can identify that. So that's the next version that's coming out. The first one's available now, and that's the second modification we're doing to this system. Is that okay for the time? Okay. So he's waving the signs up. Thank you.
Yeah, that'd be no fun.
Okay.
Good day. How are y'all? We about to go to sleep before lunch. 60-some people in here. Thank you for coming to this. I'm going to talk about several things as we go through this, but I got to list some acronyms that I may be using that you may not be aware of, okay? So, IGSHPA, the International Ground Source Heat Pump Association. Kortney knows a little bit about that, right? And we have a number of members here. How many of you are members of the International Ground Source Heat Pump Association? Excellent. Thank you. All right. CSA, Canadian Standards Association. We have a CSA 448. How many of you have that standard? We got a revision coming out. One. Okay. Y'all need to get those. All right. Particularly the newest edition that is coming out, particularly when we're talking about quality control and quality assurance. It has the standards in there for about everything, okay? I'm a voting member on the CSA, so we've watched that for several years, and we're in a final revision of that, okay? IAPMO, International Association of Mechanical and Plumbing Officials, all right? They look at codes of standards, all right? There is, in process, coming up very shortly, a set of documents and a standard for the ambient temperature loop that is going to come out. Now, not all authorities having jurisdiction have adopted these codes, but I would like to see the engineers in this room include those in your specs, okay? So thank you for that. Next one is AE, Association of Energy Engineers. I'm a fellow there, have 7 certifications, so I've been around that quite a while. So anyway, here we go. All right, this is who I am. We won't pay a lot of attention to that, okay? I'm going to talk about the Certified Geothermal Inspector. And this might be one of the best courses that IGSHPA has put together. Thank you. It's really good, okay? I don't know. Mr. Haggerty, have anybody taken this course?
There, about 15 of like that.
here in New York, okay? And that's pretty important. And you'll see why as we go through this. So we're going to talk about what these do, and we have a couple of variations and 3 certifications. 2 courses on content, and one is for the code, and that would be for the policymakers and regulators, and it's about a day long. And then we have the full quality, and that comes in 2 flavors, certified CGI and certified CGI IT in training. And so if the applicants do not have the training, then we give them a little time to get through that and then get the full certification at a later date, which is just a way to add to their file that they've done some of this training that we have. So anyway, that's where that goes. It's a good course. All right. So as we look these are what we're talking about on the code and the quality as we go through this training. Now, I've taken this off the IGSHPA website to make sure that everything is, straightforward, that you can understand what we're trying to do as we go through this. So with that, this is going to talk about the class target, okay? And we've got 12 sections. Some of them have 14, which is additional material. And there's a lot there, right? Before the people take this course, well, let me go to here. All right. This talks about, you can say second day, what it might be for the QC, CGI, okay? And then we go, after completing, you take the test, you get CEUs and so forth. IGSHPA sends those out, I do believe. Okay, you will receive that certificate. Does anybody here receive that certificate? Yay. All right. That's a good deal. All right, so before you take the course, you're given a toolbox. And that toolbox has 48 megabytes of information in it. But most important in it is a very long spreadsheet that goes through all the various nodes. And so they're all tabs. As you can go through this, and you're to be engaged from when the planning is beginning. The owner contacts the architect and engineer. You're there all the way till you turn it over to operate in the machine. And then we recommend an additional 2 years to make sure that everything is working properly. We found that extra 2 years, get all the seasons in and out, really help us understand that, okay? Here are some of the places that pre-course work will take you to. And as you can see, it goes, plastic pipe, pressure testing, a little bit of everything, okay? Fusion, which is important, right? And a lot of videos you can watch on the fusion. Okay. These are some of the videos that are in that toolbox. You can go click them, watch them, learn from them, and we hope it's important to you. And it does include grouting, okay? A bunch of other stuff, right? So these are the parts of the course, okay? So we start out with the pre-course, introduction, and then we get into the detail of all these various portions for a ground heat exchanger installation, all right? And I want to say there's been a lot of talk about tariffs, hasn't there? Well, residentially, about half the cost is the ground heat exchanger. And we need to be aware that you cannot import a borehole, okay? So we're doing that ourselves. So, that kind of ought to be a good flag for us to move forward. So we look at all this course content. We go through it. There's the last half. And 13 and 14 are optional. I always include those in my presentations to tell you all about not only single facility ground heat exchangers, will we start moving into district systems, community loops, and then ambient temperature loops. And so there's a lot of flavors of this stuff that we're out there doing, and the industry is moving pretty quickly, and we need to keep up to speed with what's happening, okay? That's what we're trying to do. All right. I'm kind of done here. And I want to thank you guys for listening. But really what I want to have you take away is documentation is the key. And knowing what the grout is, right? Was it a pump sample or a sample out of the batch? There's a big difference. And so as we go through this, there's a lot of things that we can and we do document. The in situ testing. Here in the United States, I did the first thermal response test for the industry in December of 1994 because I knew that the professional engineers, we were going to design a ground heat exchanger if we didn't know what the Earth's thermal properties were. I left that with OSU, no patent there. But anyway, we've modified that and gone to advanced thermal response testing, and that's a whole new area. So measure it, document it, and record it, and make 2 copies because somebody's going to lose the other, and hopefully it's electronic, okay? So there we are. Thank you all.
All right, great. So my name's Kortney, and I'm with Midwest Geothermal, and I'm going to talk about the thing everyone in this room hates so much, but I'm going to pull together everything we've talked about and talk about document, 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 right? We do all this quality assurance. We make sure that the ground loop goes in. What do we do with that information? It's pretty darn irrelevant if we don't actually write it down. So we need to keep all of that information, and to Garen's point, we'll make 2 copies. Invariably, the building gets sold or the information gets lost. So electronic copies would be great. I also want to highlight something that Kate mentioned when we talk about grouting and we talk about going out to a bore field, going out and watching an installation. Invite your authorities having jurisdiction to come out and watch you install. How many of us have counties or states that really don't have a ton of regulation? We don't have people that really know what we do. So invite them out. Even if they don't have regulation, or they do, invite the inspectors or the sanitarians or whomever that may be to come out and watch you install and let them ask questions. It is going to make them a better inspector, whether that's an official geothermal inspector, we hope they all are, but in any case, it's going to make them better to take a look at not only your jobs, but frankly, all of our competition's jobs too, right? Make sure we're all on the same level playing field. But we're going to start from the beginning, and I am going to say this a lot, but document, document, document. So you can prove that you've done all these amazing things we've talked about. So by documenting quality control procedures, what that's going to do is it's going to help us communicate that we've installed what was designed, what was asked of us. So we're going to go through some examples of some of that documentation that we can provide throughout the installation. Drill logs. All the drillers in this room will hate this slide very much because I require them on every borehole that we drill, and a lot of engineers do the same. But let's talk about the parts of a drill log. So at the very top, and I realize this is very small, but we're going to put the driller's information, right? We're going to put the project information, where did that borehole take place, and who put it in. Then we're going to put some borehole specific information. If you're on a commercial project, chances are you have a borefield layout that has every single one of those borefields or boreholes labeled. So make sure that your drill log matches the bore number on that drawing. Now, we have also been in states that also require a tag. So when we've worked in the state of Washington, they'll require a specific identifier. Word to the wise, do that ahead of time. So not after you've drilled 300, do they then want to reconcile the fact that I have to put a borehole tag with that borehole number. They're not the same on the drawing as it is that the state's going to require. Be a little more proactive than trying to go through 300 bore logs that are super fun and try and reconcile that. But that's where you're also going to put in maybe the information of specifically who drilled it. So above, we put the installing contractor, and then we actually put who actually drilled it and who grouted it. Then we're going to go on to the next one. This is where the actual quality assurance comes in. This is the actual borehole installation. So we're going to talk about the measured loop length. Did we get that loop all the way to the bottom of the borehole? Sometimes no, right? Sometimes stuff happens in the bore field. Something happens during drilling. We cannot get that loop to the bottom. So what did we actually get it to? Now, if we really, really can't get it to the bottom, then we're going to have to make a phone call, right? Talk to the engineer of record and see what else we can do to maybe make up that bore footage. But this is the place we're going to document all of that. So if we couldn't get it to depth, then make a note as to what did you do next, right? If it's a 600-foot borehole, we were only set it to 400 foot instead of the 600 foot. Maybe we're going to drill 200 foot adjacent to it. We're going to tie them together. Make notes on your drill log because chances are next week, no one will remember that they did that. Then we're going to talk about drilling method. So a lot of Kate's examples, we're talking about air rotary, right? Or we're using advancement of casing. That's not always the method, right? So we're going to identify here, how do we actually open that borehole open, right? And we're going to talk about whether it's mud rotary or specifically when we talk about thermal response testing or when we're doing a test bore, we really want to make sure that we tell the next person the type of drilling method we used. Because if they look at a drill log and we don't tell them that it was sonic drilled and someone goes into that with an air rotary system or trying to drill it that way, it's not going to work. So this is where we really want to be thorough about all of that information. We talk about how much bentonite that we used. So whether that's drill mud, and then we go into grout bentonite. How much grout did we use in that borehole? Tremie depth. How far down that borehole did we get that tremie pipe to make sure that we're appropriately filling that borehole, that annulus space with grout? All of that information, right? It is very detailed, but it's so crucial. Specifically, when we talk about making sure that we're properly grouting, this is where we tell that story, right? We can write down and say, I put 17 batches of grout in that borehole. Maybe the math said it only took 15. Well, we knew we had a little bit of loss, or we can talk about that a little bit more. And even as drilling contractors, that's when we say, okay, we expected it to take 15 batches. It took 30. Documenting this by filling this out, what that does now is help you get a change order for the fact that you're using double the grout. Right? I'm super annoyed when I talk about documentation, and the guys that work for us hate it so much. But why do I do that? Because it's so much easier to argue with someone when I can write it down and point to something. Prove to them the story of what I'm doing, right? They can't see it. It's all subsurface. Nobody knows. So this is where we really, truly document that. Then we go in a little bit further down and we talk about the subsurface profile. That is a fancy name for what kind of rocks and dirt did we drill through. In a lot of areas, it's the same, right? When we're going 20 foot at a time, doesn't change a whole lot. But what if it does? What if we're in an area that we get a drill log and it says, oh, we're going to hit competent rock at 10 feet and that's all it's going to be. And then you're drilling and you get down 200 foot and you haven't hit a rock yet. It's all sand. It's just terrible. So again, we're documenting to write all this down to make sure that we can prove to someone that says, no, right? We're going to prove not only what did we drill through something, but did it vary from what we originally were contracted to do. Lastly, we're going to do a pressure check. This box here in particular is great if you are just a driller. If you do not do the lateral tie-in, this is a great point of handoff to say, I pressure checked that borehole, I flow checked that borehole, everything was kosher, and then at the bottom, we're going to have a sign-off and acceptance. As the drilling contractor or the installing contractor, we're going to sign off on it, and then hopefully we actually have a geothermal inspector to be able to sign off on that as well, so that everybody understands that when we handshake off to give it to someone else, that borehole was good to go. So grout sampling. This is an example of a manufacturer's grout sampling that came back. Grout sampling specs have varied dramatically. I have seen sampling specs that require us to sample every batch. So then I have to send in a fun RFI that says, yep, that's 33,000 grout samples on that job, and that is not feasible. So let's back that off. C448 does do a great job of outlining how many samples we have, but this is the type of report that you're going to get. You'll have a date on there that it was received by the lab, the date it was collected, the project name, and then you'll get down to the stuff we really care about is thermal conductivity. Did we meet or exceed the conductivity being asked of us? Again, big deal. And then as Kate walked through a little bit, we've talked about grout sampling is a big deal. It is not a perfect process, but there are procedures to do that correctly. So again, as we're documenting, as we're doing all of this quality assurance to make sure that every one of us is doing exactly what we say and putting in awesome systems, make sure that your quality controls, whether that's grout sampling or anything else, is done appropriately. So pressure testing. So we talked about pressure testing the loop. Now we've installed a bore field. We need to keep pressure testing. We need to make sure that everything we're installing is done correctly. So this is an example of a pressure test that we're going to do by circuit. So we've installed the bore field. Let's say we have a vault. We're going to pressure test each one of those circuits from the vault or a manifold in a building, right? So best practice, at least for us, is to break this down by header. So let's say you're on a very large commercial project. What I would do is actually break this down by vault so that this particular form can be used for vault A or vault 1. And then you have all the circuits for that vault. And then you have another form that moves you on to the next vault so that you're being very intentional and specific about this vault, this circuit is what I pressure tested. And then again, we have a performed and witnessed by so that a geothermal inspector or maybe it's a commissioning agent can be there with you to validate that that's exactly what happened. Site-specific flushing procedures. So as we've talked about and seen some examples, flushing can sometimes not go great. We need to be very intentional about what we do when we flush a system. So as an example here, what I'm showing is that we actually calculated loop volume per circuit. We have the flushing flow rate that we need to be able to get the specified here, 2 feet per second minimum. And then what we say is we're going to turn that fluid a minimum of 10 times. In this example, that 10 times takes 52 minutes. So that means one direction, 10 turns of the fluid takes about an hour. But we're going to do that both directions, right? So I'm going to have on the top portion, the forward flushing plan, and then on the bottom, it's the same thing. We're just changing direction. But what this does is give assurance to the fact that you have an inspector out there. They know that you've done your homework to say that this is how long it's going to take me to turn that fluid to make sure that I'm getting proper flow through that field to get all the air, dirt, and debris out. So again, document, document, document. I know I keep saying this, right? But it's so critical. And then not only is it important for the inspectors, but how much easier is it for the field guys to say, oh, well, I can sit here for an hour, right? This flushing plan is going to take me 3 hours to do based on this system. Now, when we get into the gargantuan systems, they take a lot longer, right? But even more crucial, let's say that they're used to doing systems of this size, and then they get into 1,000 bore field. Yeah, that circuit's probably going to take a lot longer than an hour. So we really want to make sure that we are illustrating very intentionally what we're going to do to make sure that we're meeting those quality assurance goals. Last thing we're going to do is we're going to do a final hydronics test. Everything's been installed. We've done, as you can see, we pressure test a lot, right? That final hydronics test, we're going to pressurize that entire system. As we've heard, you're going to pressurize it, the US standard, right? 4 hours at minimum. And you're going to watch and make sure and calculate your pressure drop. And then you're going to record that. And then again, we've got a place for signature and a witness. So the last thing I'm going to talk about is the where is it and as-built. So we want to make sure we've done all of this work. We've made sure that it's done correctly. We've had a witness there to make sure that we've installed and done everything we said. Where is it after the fact? If it's under a building or it's under a parking lot, nobody has any idea. So let's make sure that the as-built is also part of our proper documentation. So this example of the bore field, why is this one critical? Because I have a bore that's hung out way outside of the actual footprint of the bore field. So even more important for this field in particular, I want to make sure that I'm recording where that rando bore is that's way out there. In this example, it was the test bore that we piped over. On top of knowing where the boreholes are, how many people in their as-built actually record where their header pipes are, where their lateral pipes are? Not just where they are, but the elevation. Not enough of us. And why is that so crucial to pass on to someone else? I say this every time I present, but light pole-based guys are our nemesis. Swear to God, they hit our pipes every time, like that's what they were paid to do. But we can actually take all of this data. We can use, whether it's handheld GPS software, you can go as far as buying something from surveying companies. They'll actually have it to where you can export that in an Excel format, a CSV file, that other contractors can just import into their own software and find exactly where you put stuff. And hopefully that'll help prevent somebody drilling right through and then causing more problems. But it's so important to make sure that we're documenting the entire process because we've done a lot of amazing work and we don't want to have to come back and fix it or do it again and want to make sure that client understands and loves their system for a long time. So that's it for me. So I'll turn it over.
Okay, so we'll open up the floor for questions. Anyone's got a microphone? Raise your hands if you got a question and we'll learn some more.
Thank you. Greg from Con Ed. I had a question about the installing of the piping and whether it's pull down or push down. And it was pretty definitive that you should never pull it down. But, you know, as a utility, we're kind of new to this. I've seen more people with weights pulling it down than pushing it down. So I'm just curious, can you elaborate a little more on that, or anybody else on the panel? Why so definitive of a position on that?
Hello? Okay, there we go. We use dual rotary rigs that drill very small diameter boreholes. So when we're looping a hole, we need to get the tremie line plus the loop in a very small diameter borehole. If you were relying on gravity to pull your loop down with the water in your loop, you risk stretching that loop because it's flying down the hole. But more importantly, you risk not being able to get the loop to the bottom of the hole because the weight of it itself has a lot of chance to, just from friction or, whatever occlusions are there to get caught on the side of the borehole and not get to the bottom. So if you actually use a pusher that's pushing the loop down instead of having the loop go down with its own weight, it allows you to control that insertion of the loop plus the tremie line. And that's really the only way we can get those loops in our boreholes because they're so small.
No, I'll add to that.
Oh, there we go.
I'll add to that a little bit and say that it is 100% dependent on drilling technique. So when, particularly with our company, we do a lot of mud rotary. And the viscosity, the weight of that drill mud is going to fight against us, right? So we do use weight to help let that loop go down a bit more naturally because of the same problem she mentioned. When we use too much weight or we push, we risk the chance of kinking that loop or stretching. So it is honestly a means and methods thing. So when we talk about engineers who specify this, or whether it's Con Ed or anybody else who's inspecting or specifying this, it really is a means and methods. It's really dependent on your formation and the drilling type that you're going to use. So it's a tough thing to have a hard line against.
Yeah, I want to kind of expand on that a little bit. I think maybe both. And I'll tell you why. These boreholes are not perfectly vertical. All right. We have a study at IGSHPA that was a number of sites where we're doing the borehole resistance. And so we did the caliper diameter log and a deviation log to see where they went. And then we did a suite of electronic logs. And we found that a lot of the people were embedding the borehole with the drilling fluids to a big extent, which really adds a lot of resistance to what you got. The other thing is they deviate. The borehole we used as the basis was 320 feet deep, drilled with a sonic without pull down, trying to keep it straight, high RPM, and the borehole deviated 38 feet away on that 320 feet. It was underneath the neighbor's driveway. Okay. So a little bit of both maybe takes care of both those things. Okay.
Hi, Brock Yorty, Geothermal Drillers Association. When we get into grouting testing, obviously we have on-site expectations for quality assurance, and then we also are sending off to a lab to get that thermal conductivity. Can you guys expand on how you do your on-site grout sampling for quality assurance versus sending it off to a lab?
You want to? Okay. We actually do send all of our samples to the manufacturers because it's required in the spec. So often we're sending, boxes and boxes of samples to our manufacturers, and they produce a report, just like what Kortney showed. When we do our own tests on site, and so I work for Stan Reitzma. Some of you guys might know him. He's really the guy that knows a lot about drilling, and I'm kind of passing through the message. When we test on site for our grout specifically, we'll do our own TC test. We'll pull it out of a sample from the batch. We'll do a small test just to make sure we're in the range. But that usually is more of a sanity check than an actual production test.
Garen, from an inspector standpoint, is there anything on specific gravity or pounds per gallon or anything that we're dialing in before we send off this sample to find out if we're 1.2 or not?
Sure. First of all, you want a pump sample, not a sample taken out of the bucket or the batch. It has to be pumped. And that's what you're actually putting down the tremie pipe. Okay, number one. Number two, if it's sand enhanced, in the field, a very easy way to tell what you've got is the density or the weight of the material. And so you can watch whatever your target is, 1.0, 1.2, whatever. If 1.2 is hard to pump. On that research project, the only grout that made the goal of either a 1.0 or a 1.2 or 1.6 was the graphite enhanced grout. People that come out that are grouted had a grouting unit with 600 feet of 1-inch SDR11, and that's about 800 PSI to pump it through that. Of course, there are breaks, right? So it's the pump samples, number one. Number two, the time for the carbon-enhanced grouts can be as long as 72 hours for it to build to its full yield strength. And so if you take an immediate sample, you're not seeing what you've got as a product at the end of. So you do have to wait that time. It's important to take, measurements at the site, but then again, it's important to wait until you've got the full build or yield strength of the materials you have in.
I'd like to add too, as an inspector, the other thing you can do, which is, a process of verifying that we're using the grout. Number one, you need to know what are we even trying to attain and what type of grout and what's the mixture. And you can watch them mixing the grout on site and verify. If this is supposed to be 3 bags to 2 bags, count them as they're doing it. And I've also, this is all stuff I got from the CGI course, but also how many bags were on the ground when they were done that borehole? Did they really get the grout, the amount of grout that was expected for that borehole? But as an inspector, you need to know, what is the mixing ratio? What are they trying to attain? And you can get a lot of that just out of watching the process, on top of inspecting the results of the process.
Remy Gerges, MA Engineering. I have a couple of questions quick. First, for the casing, how you determine the length of the casing? This is through the test well that they can determine the formation and to reach to the bedrock. So you get this information from the test well?
Yeah, you would usually get it from the test borehole log to see what the depth to rock is, but you'll be able to tell once you're anchored in competent rock because of the resistance against your casing. So you'll know, and the cuttings coming out, so you'll know when you're anchored into competent rock. And then to make sure that you know the depth of the casing that you're at with your tremie line, generally you mark your tremie line where your casing starts, or you measure it out and you mark it so that you know when you're starting to grout in the casing and you're out of the rock.
As an engineer, I am engineering, putting the specification. Should I list the casing depths, or?
Generally, I don't think in specifications we don't see casing depths required. You see the depth to rock that they say it is, but the requirement is that you're anchored into competent rock.
So I would say, and get a lot closer. I would say you have a couple of things. Your authority having jurisdiction is going to dictate what type of casing that you're allowed to use and how you have to seat it into the rock, 1. And 2, the type of casing that you're going to use and the depth that you're going to set it is really a means and method thing, right? So in the thermal conductivity test that you're doing, that drill log, I'd be very specific if that person, that installing contractor, actually did set the casing. Now, again, we talked about different drilling techniques, right? Sorry, I'm messing with the microphone. Some drilling techniques won't require you to use casing at all, right? We have been across the country, and there's lots of places that casing is irrelevant because you're going to drill mud rotary top to bottom, or you get competent rock super fast and you're not going to need to use the casing. So the tough part is that as an engineer, you're going to write a fine line between dictating a means and method, which is going to drive the cost up if they didn't actually need it in the first place, and then letting the driller kind of do what they do best. So I would leave it up to them.
Okay, quick second question about the sample for the grout. You said we didn't need to take a sample and test for each borehole. So what is the average to test that?
You don't need to sample every single borehole. In CSA, for 50-plus borehole installations, you have to test 3 for every 50 boreholes. That's the bare minimum requirement.
And the contractor will, or the driller will pick whatever the 3 that he's going to test it for, whatever the borehole. Do I specify which 3 boreholes, or he going to?
Well, generally you would want to test early, just because if you do have an issue, you'd want to catch it early. You don't want to be catching it at your 50th borehole.
A lot of times we'll see a specification that'll say you need to do at least 1 grout sample within the first 10 holes, and then you'll do one every 10 or every 15 after that. The problem is also, where are those boreholes? You don't necessarily dictate, again, where the drillers are going to drill, right? So the frequency, and you're going to do 1,000 boreholes, right? Then list that frequency. If maybe it's only 30, you test within the first 5, and then maybe you'll test another third, and then another third, and then within the last 5. But you can dictate the frequency and when you put them, or when you're going to collect that data. But again, I wouldn't get as specific as test borehole 3, circuit 6, because you don't always know when that driller's going to drill that borehole.
Last question about the GCI or the inspector. The inspector role during the drilling is gonna inspect each borehole, or he gonna inspect sample? What is the role?
Yeah, that if you're a CGI and you're on the location, every borehole, you have to know exact what its depth is. And so you got to ensure that the contractor or somebody use the depth gauge, not the marking on the pipe to measure that depth. Okay. And we use that a lot of times also to get the temperature profile. That's what's out there. But we've all seen jobs where short loops occur, right? And that should be, a no-no. And so that's what we generally do. That's what the CGI instruction. They should go through that. I'm telling you, it's got a spreadsheet with tons of tabs. That's really good. So I'm getting a high sign from A1. One more. Okay.
Hi, Elizabeth McCorvey, the Family Resource Center. I wanted to ask you guys if you could speak on the boreholes being close together. There's a group from Canada that said they are innovative. They do their boreholes different than others. They put them closer than the 20 feet, maybe 10 to 15 feet apart to maximize energy. Is that okay?
I could talk a little bit about borehole spacing. So it really is a factor of you want to space your boreholes, one, so that the cone of influence of that borehole matches up with what the design intent is, whether it's to dissipate as much heat as possible, retain as much heat as possible. That's more of a design side requirement. The other thing with spacing is you don't want to have borehole intersection. So depending on the geology, you might risk having more borehole intersection than others. And borehole intersection is essentially when you're drilling, as Garen mentioned, you're never drilling perfectly straight. All your boreholes will deviate a little bit, and so you risk drilling into each other. So in certain geologies, 15-foot spacing can be achieved. Sometimes we recommend adjusting the design to accommodate for maybe 2% intersection if you're doing 15-foot spacing. If you're at 17.5-foot spacing, we feel generally pretty comfortable. 20-foot spacing usually gives you a pretty good a good spread to make sure you're not going to get borehole intersection.
That's it, right? I think it's lunchtime.
Excellent.
All right. Thank you, everybody. I figured it out eventually.
Well, we do all this cool stuff. We got to work